So in this video, we're going to be looking at group 2 elements, more commonly known at GCSE as the alkaline earth metals, right? Now, group 2 elements, we need to know, of course, that they react in redox reactions where they have 2 electrons in the outermost shell and they lose these 2 electrons to form 2+ ions themselves. So what we can actually end up with is, let's say, beryllium. It loses 2 electrons to form beryllium 2+. Do the same thing with magnesium to get 2+ for magnesium, and then calcium is going to be 2+ as well. Now, in A-level chemistry, we need to be aware about where these electrons are actually coming from, and we know they're going to come from the s subshell. These 2 electrons, they're coming from the s subshell. So the 2 electrons are losing beryllium to form a beryllium 2+ ion. They're going to come from this s subshell, the 2s subshell. And then, of course, I'll go down one in the group. Magnesium is going to come from the 3s subshell, and then calcium is going to be the 4s subshell itself as well. Now, what you'll notice is of course, all of these elements in group 2, they have a similar electron configuration. The only thing that's changing is, of course, the principal quantum number, and the ion that we actually form is going to be that of a noble gas itself. We end up with a noble gas configuration in all of these cases, right? So yeah, moving on, if we were to look more specifically at the reactions of group 2 metals, we know, of course, they're going to be oxidized. Think oil rig. They're going to be losing electrons to go from a 0 to a +2 oxidation state itself. Now, we can better represent this using, of course, a half equation where, of course, I've got my metal. It's going to be any group 2 metal, to be honest, because they all react in the same way. It's going to, of course, lose 2 electrons, and it's going to end up forming a metal 2+ ion. We also end up balancing this to end up with 2 lots of electrons being released as well. You can see the oxidation state is going from 0 to +2 in this instance, and this, of course, is going to be in line with a reduction equation, which is going to happen to something like maybe a halogen or maybe a species that's going to become more negative and gain these electrons, right? So these electrons, they're going to be used, they're going to be gained by something else in the overall redox process. And that's why we can actually call them reducing agents, because while our group 2 metals are being oxidized, something else is being reduced. They're aiding the reduction of something else. Now, if you were to look at our group 1 elements, they actually follow a similar trend, similar reactivity, but of course the only difference is that they actually lose 1 electron rather than 2 electrons as before. Now, group 2 metals, the first reaction we need to be aware of is that they can actually react with water to form a metal hydroxide and hydrogen gas, which is very similar to your reactions with acids. Now, let's say I've got any group 2 metal, which I'm going to represent with the symbol M, that will react with, of course, water, and what we end up producing is that metal hydroxide, where, of course, because it's going to be 2+, I'm going to need 2 lots of hydroxide to balance this, and then, of course, I end up producing hydrogen gas itself as well. Now, in terms of this, I need to have 2 lots of water over here, and there is my equation balance, one that we need to remember, and we need to be able to apply to things like calcium, barium, and so on. Now, of course, this is very similar to a reaction that you've seen before, where if you were to look at the reaction with our group 2 metal and an acid, we can actually form a metal salt and hydrogen gas. Again, it's very similar, where you take your group 2 metal and you react that with, let's say, something like HCl. You end up actually forming, right, your metal chloride, which is going to be MCl2, and then you also end up producing hydrogen gas, another redox reaction. Now, of course, you need to remember this equation again, but that's going to be from module 2 itself. But if you were to look at these 2 reactions, you know that they're both going to be redox reactions, because, of course, the metal is going from 0 to +2, and then in both cases, the hydrogen atom is going from +1 to 0 itself. Hydrogen is being reduced. Now, if you were to assign some state symbols, normally your metal is, of course, going to be solid. It's going to be solid over here. Water is going to be a liquid, and then your hydrochloric acid is going to be aqueous itself as well. If you were to look at the species formed, right, that metal hydroxide, that will actually be aqueous. It'll be in solution, right? It'll make an alkali solution, a strong alkali solution, and then your salt will completely dissociate in this case over here, and then in both cases you end up with a gas. Now, try and think about what observations you can come up with. Of course, in both equations you will end up with fizzing because of the hydrogen gas being produced, and in both equations you will end up with the metal, the solid, actually dissolving itself as well. So you've got a very similar reaction to what you've done in module 2 for a group 2 metal or any metal reacting with an acid. Moving on, if we were to look at the rate of reaction, then what actually impacts the rate of reaction? Well, it's going to be the ionization energy. It is going to be the first and second ionization energy, but we can just focus on the first ionization energy to make things easier. Now, if I were to look at this, right, going down the group, you can see I've got a little table over here. We know going from beryllium all the way to barium, the first ionization energy, it's going to decrease itself. So the number gets more negative, right? That's what we can see. Of course, it's going to be less endothermic. We need to put less energy into the system to make the reaction happen. Now, if you were to look at this, the rate of reactivity with beryllium, we actually end up with no reaction. That's how high the ionization energy is. If we were to look at barium, the reaction actually happens quite quickly. Now, this is because we know that, of course, our metals, they're going to react in oxidation reactions where we end up forming a metal 2+ ion and then 2 electrons, and the energy required to remove 1 electron, or the first electron, the highest energy electron, is going to be, of course, pretty similar to the first ionization energy itself, and then of course the second ionization energy. That's why we can actually use this information on the first and second ionization energy to tell how easily a metal will react, or in other words, how easily this metal will lose these 2 electrons itself. So yeah, the trend and the explanation is pretty much the same as ionization energies then. So if you go down the group, right, we know of course the number of shells is going to increase, and what that means is that shielding is going to increase. If of course the number of shells increases though, we also know that of course we end up with a greater number of shells. So beryllium has 2, magnesium has 3 shells, calcium has 4, strontium has 5, and barium has 6. If we were to look at the number of shells increasing, we also know our atomic radius is going to increase down the group. If we were to look at nuclear charge though, we end up with more protons. So I've got 4 protons for beryllium, but then I look at barium and I've got 56 protons. You can see the number of protons is increasing, and that actually increases our ionization energy. But because of course shielding is increasing and atomic radius is increasing, we know them 2 factors outweigh the increase in nuclear charge, but we still have to mention it to the examiner, just like we did with of course our ionization energy trends. So yeah, that's nuclear charge done. Again, we're just following the points of NANCARs where we're talking about this in terms of shielding, atomic radius, nuclear charge. The last point is of course going to be nuclear attraction. Nuclear attraction overall, that is going to decrease, and that means of course it's going to require less energy to remove these 2 electrons itself. In other words, it's going to need less energy to be oxidized itself, and so it ends up being more reactive. So yeah, that's the trend in reactivity for our group 2 metals that you need to be aware of, especially with their reactivity with water. What about the last 2 reactions that you need to remember? Well, of course, you know that group 2 metals, you might have seen this at GCSE, you can actually burn them in oxygen and you can actually end up producing a white powder itself. The bonding is going to change, and of course you end up with a metal going to form a metal, and then it's going to be an oxide itself. So I can take something like, again, my general metal, I can react that with oxygen, and I can end up making a metal oxide, which of course oxygen is -2, the group 2 metal is -2, and so overall I end up with something like this. But if I were to balance it, I end up with that. Again, our metal is going to be solid, our oxygen is going to be a gas, and then our metal oxide is going to be a solid as well. Now in terms of this, of course, for things like magnesium, you've probably seen that before, that would form a bright white flame itself. Now in terms of an example that you might have seen before, you might have seen something like magnesium being burnt in pure oxygen in a cylinder of oxygen, and that makes a bright white flame itself. If we were to look at our group 2 metal oxides then, so this is a compound of our group 2 metal, we can actually react that with water, we can dissolve it in water, apart from magnesium because that's quite unreactive, but we can actually form metal hydroxides this way as well. So it's another way to make a metal hydroxide. So what we can actually do is we can take our metal oxide, which of course I'm going to draw out over here, and we can react that with water to make it dissolve, and what we can end up producing is a metal hydroxide itself. 2 lots of hydroxide there again. Of course, if I wanted to make this balance, I've got 2 lots of hydroxide on the right, 2 lots of hydroxide on the left, and that balances on its own. So again, 2 equations that we need to remember, as well as of course the condition that we actually end up producing when we dissolve that metal oxide in water, that actually makes a metal hydroxide, an alkaline solution itself. Because that metal oxide, remember, it's solid. water, it's going to be a liquid, and then the metal hydroxide, in most cases, it's actually going to be aqueous itself as well. Now, when we look at our trend in terms of metal oxides and their reactivity, that actually is going to be the same as, again, ionization energies, where it's going to increase going down the group. The ability for a metal oxide to dissolve in water is going to increase going down the group, and what this results in is, of course, our metal hydroxide being more soluble. If it reacts with water, it's going to be more soluble, and of course you end up with a stronger alkaline solution and hence a higher pH itself. So if you look at barium hydroxide and you were to compare that to something like magnesium hydroxide, barium hydroxide, that's formed from barium oxide, of course, and of course you end up with a faster metal oxide reaction. You end up with a more soluble metal hydroxide being formed, and then you also end up with, of course, a stronger alkali and a higher pH itself as well, right? But again, if you were to look at your normal trend, reactivity is increasing, first ionization energy is going to be decreasing itself, and so overall you end up with a faster reaction and a stronger pH. So yeah, moving on from that, then I've got a task for you to do. Feel free to pause the video and have a go at the following. Again, you're just recapping some reactions with the main products that you actually get. We don't really want any byproducts, and then of course your reactants where needed as well. So yeah, I'm going to start off over here. I'm going to go with calcium because that's a bit more easier. If I react calcium with an acid, remember we make a salt. A salt is when the H plus of an acid is going to be replaced by a metal or an ammonium ion. So I end up making calcium and then chloride itself. That's the first one done. What about the next one? Calcium with water. Well, remember, we can end up making calcium hydroxide this way. And of course, we end up with something that looks like that. What about calcium reacting with something else to make something that could make calcium hydroxide? Well, of course, we could react calcium with oxygen, and what we can end up forming is calcium oxide itself, which we know can react with hydrochloric acid to form calcium chloride, and it can also react with water to form calcium hydroxide. So there's them 4 easy ones done over there. Now, what about the next one then? Calcium carbonate. Well, a metal carbonate can react with, of course, hydrochloric acid, and we can end up forming a salt, and then we also produce carbon dioxide as well. In this case, the salt is going to be calcium chloride because, of course, I've got hydrochloric acid over here. Now, another reaction that you come across at GCSE that you need to know for A-level is you can take, of course, a metal carbonate, you can heat it up, you can end up with thermal decomposition to form calcium oxide itself as well. Another one, calcium hydroxide going to form calcium carbonate. Well, of course, you're going to need to react calcium hydroxide with something, and that something to make this calcium carbonate is going to have to be carbonic acid, which is H2CO3 itself. And there's that last one done, a bit trickier than, of course, the others. So moving on, right, we need to be aware of some uses of our group 2 compounds. And if you were to look at the first one, calcium hydroxide is actually used in the form of something called slaked lime, and it's actually used in rice and paddy fields. It's used in agriculture, and that's used to neutralize acidic soils itself. Remember, it's going to be an alkali and it's going to react with an acid, and you're going to end up with a neutralization reaction. Looking at the next one, you've got magnesium hydroxide or calcium carbonate. These are actually used in indigestion tablets. They're used as antacids, and they work by neutralizing excess stomach acid itself. And then in this example over here, this Tesco fruit flavored indigestion tablet, you've got here calcium carbonate as the active ingredient. That's going to neutralize the excess stomach acid. And the final one over here is, of course, going to be for a barium meal, and barium meals, they actually contain the active ingredient, which is going to be barium sulfate, and that's going to be insoluble. And what it does is of course, it coats the inner workings of your digestive system, your small intestine, large intestine, and that actually shows up on the x-ray along with bones and stuff as well. So moving on then, I've got a task for you to try, and it's just based on, of course, some exam questions, some multiple choice exam questions and a short answer question. Feel free to pause the video and have a go at the following. Resume once you're ready to move on. So yeah, moving on, we're asked to state whether the following are going to be true or false. The second ionization energy of magnesium is going to be greater than the second ionization energy of calcium. Now, when we look at it, we know, of course, we've got magnesium and then we've got calcium underneath it. We know, of course, going down the group, the first and the second ionization energy, they're going to decrease. Why? Because, of course, NANCARs, the number of shells is increasing, so shielding is increasing. So, of course, you know that the atomic radius is increasing. The electrons, of course, they feel less nuclear attraction, and so the more easily lost itself. So we know that, of course, that is going to be, of course, true, right? So that first one is going to be true. What about if we were to look at B? A strontium ion Sr2 plus contains a total of 6 electrons in its s orbitals. Well, if I were to look at strontium, right, we know, of course, strontium is going to be in period 4, and we also know that we would end up with, of course, 1s2. We'd end up with 2s2, we'd end up with 3s2, and then, of course, we would end up with 4s2. But the thing is, if we're looking at a strontium 2 plus ion, we've lost 2 of these electrons. So we do actually end up with 6 electrons in, of course, all of the s orbitals put together. That's the total. So, of course, that one is also going to be true itself as well. If you were to look at the next one, the equation for the reaction of barium with water is going to be that. Straight away, quite hard to spot this one. This is going to be wrong. This is actually going to be false. And the reason why is because, of course, barium reacts with water, and we actually don't produce barium hydroxide like that. We actually produce barium and then, of course, hydroxide like this. This is the formula of barium hydroxide. So in that case, this last one is actually going to be false. And I think the examiner, they actually wanted all 3 of these to be right in that 1 mark multiple choice question. So looking at the next one then, a student adds magnesium to dilute hydrochloric acid in one test tube and does the same thing to another test tube but with calcium instead. Now the examiner is asking us to suggest 2 observations from the student's experiment that would show that calcium is going to be more reactive than the magnesium itself. Now in order to answer this, I need to think about my observations from this experiment generally. We know, of course, our metal, that's going to be a solid. That's going to react with, of course, hydrochloric acid, and that's going to be aqueous itself. And we end up producing our metal chloride in this case, because it's just an acid and a metal reacting together in a redox reaction, and that's going to be aqueous as well. And then we also end up forming hydrogen gas as well. Now, if you were to look at it, right, there's 2 things happening here. Our solid is going to dissolve in both of these reactions, and then we're also going to end up with fizzing because we're producing a gas. But of course, calcium is going to be more reactive than magnesium. So with calcium, what we expect is faster fizzing, because of course we're going to produce the same amount of hydrogen but faster. And then our metal itself that dissolves, we know that our metal is going to dissolve faster, right? So in that case, we need to say the following to get 2 marks in the exam. Calcium fizzes faster and calcium dissolves more quickly itself as well.